In this video, I'm going to build a sentiment analysis model from scratch using gradient boosted methods. So whenever we think of text or NLP data, the few of the algorithm that comes to our mind is TF-IDF, count vectorizer, or neural network models, sequence models like LSTM, bidirectional LSTM, and other neural network models. Now, if you see in one of my video, I developed an sentiment analysis model from scratch using TensorFlow and using bidirectional LSTM. You can click the link on the top and watch it. But what we saw is even with some complex 4-layer network, it was like 4-layer bidirectional LSTM. It took around 45 minutes to train on a GPU, and the maximum accuracy we got was around 90%. So now we can go and increase the complexity of the model further by adding layers. But at one stage, it depends on the more data we feed in. Even though our data set was quite decent sized, I will not call it very big, we saw like basically the accuracy kind of saturated at 90%. Now we have to look at building pretty higher size data set and feeding to the neural network to get even better accuracy. Now, and the second aspect is whenever we talk about sentiment analysis model, it's not only unstructured data like text. Sometimes we may have to substitute it with structured data. A typical example is a call center sentiment analysis. So whenever in call center we get voice data, we convert to text, and then we do sentiment analysis. But we also have a lot of tabular structured data like the call wait time of the customer, the number of call transfers the customer had to go through, the number of times the customer was put on hold, and there are a lot of other structured attributes that comes along with call center. While we can still use neural network, but these kind of data set fits a traditional machine learning model better. There are multiple aspects to it. You don't need to have a very large data set because some business are constrained on size of the data that is available. The second thing is you also get better explainability of the model on what kind of text is contributing to negative or positive sentiment. So in this case, we are going to use a GBM model, and I'm going to show like how you can get an almost similar accurate model has the neural network model that we had trained. And at the same time, in the next video, I'm going to go into the details of each and every feature and talk about the explainability aspect of it. So let me get started. Some of the cells I have already executed because the installation might take time. But I will just quickly explain it before I get started with the executing the core part of the code. So what I'm doing is I'm going to use H2O in this case, H2O based GBM models in this case to train the model, but you can use any GBM model. It can be a scikit-learn, it can be a Spark machine learning GBM. You can use any of those. The reason I'm using H2O is H2O GBM more efficient and faster than the scikit-learn version, so we can see the training happen quickly because I'm going to show each and every step of the training, increase the complexity of the model, feed in other attributes, and then see how the performance behaves, right? So I'm installing Java for that because H2O is dependent on Java. In fact, it's written in Java, so I need a Java installed. So that's what I'm doing in the first two steps, and then I am installing H2O version 3.30. 0.1. This is the latest stable release, but if you want, you can just give H2O and it will download the latest version available. I am also importing TensorFlow datasets. I'm not going to use TensorFlow in the model, but I am importing TensorFlow datasets to fetch a Amazon review dataset that is available pre-built rather than downloading the dataset and uploading it. Then I am importing H2O, which I am going to use for modeling. I am importing NumPy. I am starting the H2O cluster. H2O.init will start the H2O cluster, and that cluster is what we are going to use to train the model. You can see basically the cluster is up and running, and this is not a GPU based system. This has regular CPUs only. So basically, you can see here I have just two cores of CPU available. In case of neural network, we had to use a GPU based cluster, otherwise the training will take forever. Even with GPU, it took around 45 minutes to do one iterations of one iteration of training with 5 epochs, right? Then what I'm doing is I am using the TensorFlow dataset load method and pulling in the Amazon reviews personal care appliance data from there, and then assigning the dataset to train dataset. So what is going to happen is when we call this TFDS as a set of predefined dataset in the library, and Amazon US reviews is one of them. Within Amazon US review, there are multiple dataset. You have books review, you have electronics review. I'm specifically using personal care appliance as it has like a lesser number of records compared to others, but still a decent size. It has around 80k records. We'll see the output. It has around 80k records over there. So that's what I'm doing. I'm pulling the data set into a train dataset method, and then till here I have run the code. From now, let me start running. Let me quickly print the info of the data set. So in the info of the data set, basically you can quickly see like you have the customer ID, review ID, product ID. The column I am going to use here is the review body, which contains the full review text. So when you go to Amazon, you buy a product, you go and enter your review over there. So this review text will contain that review. The review headline is also something we are going to use, which will contain the basically a small headline that you give for the review, right? So we are going to use that. We are also going to use the helpful odds variable, which is like a structured variable. It basically, when you review it, people will vote whether their review was helpful or not. So we are going to use that particular value. And the star rating is the rating between 1 to 5 that you give on Amazon. So 1 is basically the lowest rating and 5 is the highest rating. We are going to use these 4 variables in our data set. Now coming to that, what I'm going to do is I'm going to first take the data set. The TensorFlow data set is in TF data format, but to run a GBM model or a regular machine learning model, I need it either in pandas or numpy. So I'm going to take the trained data set that we had and convert it into a numpy. So I'm using TFDS provided as numpy method and assigning it to a data set. So that's what I'm doing over here. And let me quickly print the data set over here, which will show a few rows as output. Now if you see over here, you have the review body, which I spoke about is the complete review of that particular product. You have the review headline, which is a short description of that particular review. You have a star rating, which is a rating between rating between 1 to 5. 1 is lowest and 5 is highest. And the helpful odds is on the top, where it just show like how many people found that particular review helpful, right? So that is on the top. Now, once I have it into numpy, what I'm going to do is it gives a numpy ND array as output. So I'm going to pick each and every these 4 columns that I'm going to use. You can see helpful odds, review headline, review body, star rating into 4 different variables. And based on these 4 different variables, I'm going to create a H2O data frame. So H2O data frame. H2O data frame is similar to pandas data frame, but since I'm using H2O, I'll create a H2O data frame. And what I'm doing is with the H2O frame, I am taking these 4 variables that I've created on the top. I'm doing a numpy array.hstack to combine these 4 variables together. It is similar to how you use numpy, multiple numpy variables in pandas. It is very similar to that. The syntax is exactly similar. The only thing is instead of a pandas data frame, you are using H2O data frame. And I'm telling the column names as odds, headlines, reviews, and rating. These are the 4 columns I'm picking up. And I'm just giving a data type over here, like numeric, string, and other depending on the column. So these are the 4 columns I'm picking. I'm creating an H2O data frame now. So once that is happening, let me also print H2O data frame to see how the output looks like. So basically, you can see the output over here. You can see the votes is the 0, 3 and all, the headline. So now we have kind of a structured format of the data. You have the reviews, you have the headline, you have the rating over here. Right now, next what I'm going to do is see if you see the rating is actually between 1 to 5, and when I want to create a sentiment analysis model, I basically wanted to put it at 2 levels, 0 for negative sentiment and 1 for positive sentiment. While that is not important, you can still run a multi-class classification, but in this case I want to just reduce the sentiment to positive and negative. So what I'm doing is the target column I'm creating, I'm using the rating column on top, which is between 1 to 5, and I'm telling if it is greater than or equal to 4, then make it 1, else make it 0. So what will happen? The rating 4 and 5 in this case will become 1, and the rating 1, 2, 3 will become 0. So if you see over here, This is the last column that we have, the target, and whenever there's a rating 4 and 5, it's 1, whenever there's a rating 3, it's 0, right? So basically now we have our data frame. Let me quickly print the shape 0, which will show the number of rows in this particular data frame. There is around 85,000 rows. As I said, it's a decent sized database for us to run the models. It is still not pretty less. Even GBM model can handle a decent sized data set. Now the next is I'm just checking the target distribution. I can see like the positive sentiment is the majority class, so around like 62,000 records are positive and 23 are negative over here. So it's kind of an imbalanced data set, but not very highly imbalanced. It looks like it's like around 1 to 2.5 ratio, right? Let me quickly do a describe as well. The describe will print the column and also show you descriptive statistics, so you can go on the top and you can get for all the numeric column. It's showing you like what is the mean, max, and sigma value and everything. So just showing you output. If you want, you can just go to the descriptive statistics. Now what I'm going to do first is, typically when we build an NLP model, we have to tokenize the data, right? And then we remove the stop words. So that's what I'm going to do now. So for that purpose, what I'm going to do is I'm going to import the NLTK package, and then I am going to import the stop word corpus and download the stop word corpus. And basically take the dictionary over there, English dictionary of stop words, and assign it to a stop word variable. Right, and then I'm creating a function. Let me quickly run the next 3 lines and discuss on this, because the next couple of lines will take time. So let me run this. So what I'm doing in the tokenize method is basically I am taking input review and headline. So we have 2 columns which have text. If you see on the top, we have review. We have headline. Your headline is this, and the review. These are text columns. So what I want to do is I want to take this and tokenize it first, and then I want to remove the stop words from it. So that's what I'm doing over here. In this function, I am basically calling. I'm basically passing the reviews and headline, and then here I'm tokenizing by the word. So each word will be an token. It will just delimit by the words, and then I'm doing a 2 lower because I want to make sure like all the words that start with you need to capitalize and the normal word are treated similar. So I'm doing a 2 lower, and then what I'm doing is any character that is less than 2. I'm just ignoring it because I don't want 2, 8 and all these variables. So I'm just ignoring. I'm taking only words that are greater than 2. And finally, what I'm doing is I'm in the filter, tokenize filter. I am basically telling where that particular value is not in the stop word list. So that's what I'm doing over here. So finally, it will return me the final filter, a final tokenized and stop word filtered value as output. So now what I'm doing is in the word reviews, I am passing the H2O data frame which I created on the top reviews method, and I am tokenizing the value. And then in the bottom one, I am passing the headline and then tokenizing the value. So I will have a tokenized word vector, and I will have an of the review. I will have a tokenized word vector of the headline variable. I am just printing these 2. It's going to take some more time. It should be done anytime sooner. The reason is it has to go through all the text and print the head. So it's going to do. So while that is getting printed, next what I'm doing is I'm importing H2O word to vec package. What I'm going to do is I'm going to take this particular word vector that is there, and then I'm going to create a word embedding out of it. And for creating the word embedding, I'm going to use the word to vec package. So the word to vector package does is it basically tries to map a word using a dictionary of vector. And then I am importing 2 estimators. I am importing gradient boosted estimators and then the XGBoost estimators. So these are the 2 estimators I am importing over here. So now if you see on the top, the reviews is there. So what is happening is it creates like all token and gives you the word. So you can see basically the reviews has glasses, excellent, values. So basically it has taken all the word, it has tokenized it, removed the stop word, and then printing it. Similarly for the headline also. Right. So we have no 2 word vector over here. Now the thing I'm doing is, now I'm taking it, you can see basically the vocabulary for reviews as around like 2.79 million records. Basically the 80,000 reviews contribute to so many 2.79 million records. So I have imported this to package. I'm going to create a word-to-vec model now. So in this case, what I am going to do is, I have already created the word-to-vec model, but in case if you want to create it, you can use this command. I'm creating a word-to-vector estimator and mapping the word-to-vector estimator to an 100 vector size. All right, and then what I'm doing is I'm training the model based on the word review dataset which I created on the top. So I have word review and word headline. I'm first using only the word reviews to build my model, and then I will use the word headline along with the word review. So that's what I've done it. Now this training is going to take time because it is going to take the vocabulary and create a custom model for you. So what I've done is I've already created it and I have downloaded this model w2v.amazon.model. I'm just going to load that over here. So this model is already there in my folder. If you see the folder over here, I have already trained it and then I have uploaded the particular model over here. Just a minute, it's taking time to come. So yeah, so you can see the W2V Amazon model is there. So that is the model I am loading over here. Now just to see the sanity check the model, what I can do is I can use the word-to-vec model and find synonyms. We know we are in the personal care appliance. So the personal care appliance can be electronic toothbrush, or it can be hair dryer, or it can be some contact lens cleaner, right? So I'm just telling like, okay, find synonyms for perfumes. You can see like ammonia, fragrance, wintergreen, that is a flavor, scents, and these are all like closest neighbor for it. Similarly for toothpaste and for glasses. So you can see basically the word vector has learned the embedding. Now what I have done here is, right, if you see the word-to-word algorithm, what it does, it takes a text corpus as an input and produces the word vector as output. That's what it does. So the algorithm is first going to create a vocabulary from the training text data. So in this case, I have the training text data, word reviews. It's going to create a complete vocabulary from that and then learn the vector representation of those words. Now the vector space can include hundreds of dimensions. So what I'm doing is I'm only picking the first 100 dimensions out of it. That's what I'm doing. One good thing about word to vector is, so the word that shares similar context in the corpus are placed in close proximity to one another in the space. So that's why you are seeing when I do a find synonym, a lot of these words are better shown and better represented. Rather, if we do a TF-IDF or a count vectorizer, we are losing the context of the word. But in this case, the context of the word is maintained. Now, if you remember the neural network model I spoke about, the very first layer I had in the bidirectional LSTM model was a word embedding layer. Now, we were telling the neural network model to learn the word embedding in that case, and that also creates something similar. But if you don't want neural network to do it, if you want to use a pre-trained model, I can also use this word to vector model that I created to print the matrix embedding and then pass it to the neural network. That can be my first layer as well. Right now, I have trained the model. What I'm going to do is I'm going to transform my word vector over. So what I'm doing is I'm calling that vector model.transform. I am taking the word reviews and then I'm calling the aggregated method as average. I'll come to that. So what it is going to do is it's going to let me the next few records so that you can see the output. So it's going to take the word review and then it's going to convert that into a more like a vector representation, numeric representation that my model can understand. My model cannot understand the typical string or object columns, right? The words. So we need to give it a integer representation, and that's what the transform method does. See the output. So the output is from column 1 to column 100 over here because we have limited the vector size to 100. Now there are two ways to aggregate. One is don't aggregate. When we don't aggregate, when we say none over here, then each input word is mapped to a single word vector. But what we are given is we are given average. So what happens in the average is the input is treated as sequence of words delimited by each sentence. So, and what is going to happen, each sentence is mapped to a vector and the vector belonging to the same sentence. So we have one sentence, right? Those are averaged over here. So basically we get rather than having each each word as an output. We are just averaging it across a sentence, and that's what the average method does over here. So now we have this. What I'm going to do is I'm going to create a new data frame, calling it as H2O DF extension, and I'm going to take the H2O data frame that we had, and I'm going to attach the review vector column, that is the vector column that we created on the top. So I have this. Then I'm going to take this as my data frame for training the model. Now what I'm doing over here is I'm doing an basically a split data frame and telling a 80 ratio. So 80 ratio will be training, 20 ratio will be validation data frame, right? And if you quickly check the validation data frame output target variable, you can see basically the target column has 12,000 positive reviews and 4,000 negative reviews. This validation. Similarly, training will have the remaining data. Now I'm going to create an GBM model first. So the very first thing I'm doing is I imported the GBM gradient model on the top. I'm using that. I'm not giving any tree size or limit. What I am telling is you stop the model when you are seeing the tolerance level between last 5 window size. The stopping rounds is less than like 0.001. So that means when my model is not learning, stop the model. And this I am calling it as a baseline model. So first I am creating a baseline model. Let me quickly run this, and I am passing the input as the review vector dot name. So the review vector dot names, if you remember, it is nothing but the column name C1 to C100. So I am passing C1 to C100. So if you see over here, this is the review vectors dot head. When I say dot name, it's going to take the C1 to C100 column, and it's going to pass only that column. The first model, I'm not passing anything else. I'm passing only the 100 word to vector embedding we learned, and the target column is the target column 0 or 1. Basically the target column 0 or 1, and then what I am doing is it's completed. Let me print the AUC, and then let me complete these both. Yeah, and then I'm giving my validation data frame. I am telling the validation data frame score interval is every 10 trees you score it and check how the performance is. So now you can see basically it has produced a model with a AUC of 0.87, which is not bad. This is just a baseline model for us. And if you see the confusion matrix over here for this model, you can see the positive class, which is the majority class, has been pretty good. The error rate is only 0.049. But the negative sentiment class, the error rate is 0.48, which is slightly higher, right? So what I'm going to do is I'm going to keep on increasing the complexity of the model. That's what I'm going to do. So we know that the class is not balanced. We know like the positive class and negative class is not balanced. So H2O gradient boosting, let me run this 2 cells as it takes time and then talk about it. So H2O gradient boosting has a method called balance class equal to true. And what I'm doing is I'm just added that parameter balance class is equal to true, and the GBM is going to check whether to undersample or oversample, and basically take a call based on that. So let me see if the balancing the class really helps. Sometimes it helps, sometimes it does not help, right? So first thing I'm going to check that because in this case what has happened, the positive class is good, but the negative class we are seeing high error rate. So balancing might help. So let's first wait for this model to complete and check it out. Now it's almost getting complete. Once this particular thing is done, if you see over here, now the AUC is still same. Like it's kind of a 0.87, and here if you see basically in the top it was 0.4835, it became 0.4829. No major difference over here. So basically the balancing is not working. So now let me go and let me try to add a few additional columns. So one of the column that we had was helpful votes, which is a value on how people find helpful your rating is. So what I'm going to do in this case is, let me again run this and let me come back to that model. So what I'm going to do this, along with the review vector dot names, I am also in the votes column. So this is going to take the votes column. It's still running the same hyperparameter. I have not gone to the hyperparameter at all. Still my matrix is AUC, the stopping tolerance is 0.01, and then basically my stopping rounds is 5, right? So now if you see after adding that, still there is not much improvement on the accuracy of the model. It's 0.87 and it's like 0.4835, right? Now what I'm going to do is I'm going to add the headline column as well, and then you'll also see the interpretation of the model to some extent. So to add the headline column, again I need to go to my word to vec model and call the transform method of words headline that we created on the top, and I'm calling the aggregate method as average. And then what I'm doing is, since we see it's going to create column names again C1 to C100 because 100 is our vector size. But in this case, since I already have C1 to C100 assigned to my regular word body, I am going to add headline underscore the word name. So it creates headline underscore C1 and headline underscore C2. Let me run this, and you can basically see the output. It's going to create headline underscore C1, headline underscore C2 and C3, and I am going to combine this my regular word to vector, regular extended data frame. So my extended data frame add C1 to C100. Now it's also going to have the headline C1 to C100. So that's what I am doing. I am combining it with my extended data frame. Let me quickly print the extended data frame so that you can basically see like how the output looks like. So I'm just going to call the head method, and basically if you go on the top, you can actually just 1 minute. You can actually see all the review votes and all the C1 C2 to column is there. And but if I go to the towards the end of this particular data frame, you can see all the reviews. And let me go towards the end of the data frame. Let me quickly drag it, and let me again go on the top. So you can basically see over here. Just 1 minute. My system is slow. Yeah, you can see all the headlines and C92, C93 as well. So now we have a data frame which has the headlines, which has also the regular body of the text and everything. Again, since I am now added a new value, again I'm going to split the data frame into 80-20 ratio, and then again I'm going to have the same hyperparameters. I am assigning to GBM underscore all columns. The hyperparameters I am not changing. Now let me run these two and let me explain what I am doing. Right. So now what I'm doing is, apart from the votes and review vector names, I am also adding headline vector names to here. So now let me see after adding the headlines along with the regular review. Right. So what I'm doing, I am having one structured data or tabular data votes. You can have multiple tabular data as well. Just for this demo, I'm showing one. Then I have two text columns. One is the headline that a user gives in the review. Second is the review body itself, that's a detailed review. So that's what I am having. I'm concatenating all three. I am again like training a GBM model, and after that what I'm doing is I'm going to print the AUC value of this particular model and then the confusion matrix. And now if you actually see on the top, so basically, yeah, it's here. Now from 0.87, the AUC has gone to 0.92, which is a substantial jump, right? And in fact, our neural network model, which was like 4-layer complex bidirectional LSTM, was stuck at 90. Right? And if you print the confusion matrix, now if you see from 0.48, it has come to 0.37, and the positive sentiment class is almost like holding on to same. So basically, we can see definitely adding the headlines also gave a lift. And now you can see the output. What has happened is, this is the scoring history. It has basically created up to 50 trees. And the 50 trees is what that's a stopping round kickoff, and it stopped. And if you see the variable importance plot of this particular model, you can see the headline column that we added like headlines out of the 100 embedding, the 90 and 53 are contributing to the outcome. Apart from that, the regular text column is contributing to the outcome also, but for some reason the votes column is not contributing much. It's not in the top 10 variable importance, right? So now we know, okay, the 92 is, but now can we do better? Now what I'm going to do is I'm going to start running for different hyperparameters, right? Now I can do a grid search or a random search, but just to see whether the top model was for 50 trees by default. Can I increase the trees to 100 and max step SIPs and learning rate rather than doing a stopping metrics? Can I do it that way? So that's what I'm going to do over here. So what I'm doing is telling like, okay, rather than training 50 trees in the default, train for 100 trees. So I'm forcing it without any metrics, right? And the depth of the tree is 6. I will show you how to do a random search in H2O. I'm not going to run it and show, but I'll quickly show you so that if you want, you can do a random search. And next, what I am doing is I am if you see here, I am having the headline vector and the review vector. I have taken the votes column out because I didn't find anything it contributing it, right? So let the model run. Let this model run and let's see the output. If we are seeing any better improvement than 0.92 we got with setting the entries to 100. If we get some accuracy, then maybe we want to increase the complexity further and maybe try with 200 trees, right? So that's what I am going to do. And now after what I'm going to do is, we know typically XGBoost is it's kind of an faster version of GBM, right? Now GBM takes time to train the model, but XGBoost is very fast because of the way it is implemented, because of the parallelism and everything. So for the same hyperparameter, I'm going to run a XGBoost model. Typically everyone say, okay, use XGBoost, the performance will be better than the GBM model. But let's see if that claim is true. It cannot be, in some cases it can be true, but not in all cases. But definitely you can see XGBoost is very fast. So rather than training a GBM model and waiting it, you may want to train a XGBoost model. That's what we are going to try next. While this is running, I'm going to print the confusion matrix. I'm going to also print the scoring history to see how much trees it created, and then I'm going to go to an H2O XGBoost estimator where I'm going to give. So if you see with 100 trees, you can see there is further lift. So rather from 0.92, it has come to 0.93. So you can see a small percentage increase in the performance. And in fact, you can see the negative class has performed better. The positive class has slightly gone higher, but the negative class error rate has significantly come down to 0.30. So basically increasing the number of trees really makes sense. And if you see the scoring history, you can see now the model is trained for 100 trees rather than the 50 trees earlier. Let me next run a couple of lines and let me quickly see whether XGBoost does any better. Let me run this and let me show it to you. So what I'm doing now is, rather than using a GBM, I'm using XGBoost for basically 100 trees and learning rate 0.1, max leave 6, and then I'm just giving a tree method ID string. A good thing about XGBoost is it can run on GPU as well. If I move east to GPU east, then you can see how fast the output came when you are training with XGBoost. It was pretty fast for the same hyperparameters and same iteration. And you can see I see a drop again in the AUC to 0.92. Maybe I want to try with a larger tree size because of the parallelism, right? It is quite possible that it may take more number of rounds to converge better model. And you can see the error again increase from 0.0 to 0.38 with the same hyperparameters, but the positive sentiment class is better now, right? But that's an option. Again, if you want to use XGBoost and try it out, you can try it out. Now finally what I'm going to do is, now I know exactly my GBM model works, right? Now I want to I add only the train and validation set, but I want to create a separate test set. I want to increase the trees to 200 and I want to try it out. So that's what I'm doing over here. I'm taking my data frame and splitting into 3 frame, right? I'm doing a 70% for train, 15% on validation, and another 15% by default will go to the test. So let me run this, and then because it's going to take time, let me run this training and then I will talk about this. So now what I'm doing is I'm creating a estimator with 200 trees, max node depth 6, and then I am running the model. I'm going to see how finally the output looks like. Now rather than running it manually, I can also do an random search. So this is a bonus. I'm not going to run it and show because it's going to take time. So in order to run an random or grid search, what you can do is you can define your hyperparameter space. Here I am telling run for 100T, 200T, 250 the depth of the tree is 7, 8 and different learning rates. And I'm creating a hyperparameter and search criteria dictionary where I'm giving the hyperparameter as this list that I created. And then I am importing the H2O grid search package. Now the grid search package, I'm calling the gradient booster estimator. I'm passing the hyperparameters to search and the search criteria. In the search criteria, I'm given random discrete. So random discrete is for random search. If I don't give random discrete, by default, it's going to do a grid search. It's going to search across all the hyperparameters. And then the max model, I'm telling for 4 models, right? Once I have that, I'm going to pass my training data as earlier. I'm going to pass the headline vector and I'm going just sorting by the AUC metrics and I'm getting the top model that is performing. That's what I do for random search. You can also use H2O or ML in this case. rather than using the grid search. If I want to use the same data set that I prepared, but I want to run it across multiple models like XGBoost, GBM, and then linear regression, SVM, or I want to use a stack classifier, I can kind of use H2O AutoML to get that. In fact, I have a separate video on H2O AutoML. If you want to try it out, you can try it. The link on the top, and then you can just put that into action over here. Now our model is going on still because I gave for 200 trees, and we saw basically GBM model takes time. It's still running. While this is running, I'm going to print the AUC, I'm going to print the confusion matrix, I'm going to check the model performance on the H2O test. So what I'm doing is I have built my model training data frame, and then I have used validation data frame to validate it. And finally, what I'm going to do is I'm going to use the test data that I created over here, validate the actual performance. Now I may have pretty good accuracy in the training, and the validation data frame is also seen, but I want to pass an unseen data set to this particular model and see how it performs, and that's what I'm doing here. So I may get a model with 90% accuracy or 95% accuracy. In the test data set, if it comes like 80% or 85%, it's not worth it. I want to see my model generalizes better, and that's what I'm doing over here. And finally, I'm going to print the variable importance plot. I think the training is almost done in a few seconds, and then we can see the output is the training is done. Now we are seeing the accuracy has gone slightly higher. Let me go on the top. Yeah, we are seeing the accuracy has gone slightly higher to 0.939, close to 0.94. And if you see the basically the negative class which we have, which is like not slightly imbalanced, the error has come down from 0.30 with a 100 tree depth to 0.27 when it's 200 tree depth. And then basically I'm just printing the performance result of my H2O data set, H2O test data set, and you can see even with the test the AUC is holding on to 0.93, and you can see the confusion matrix is pretty good. Even though the negative class is 0.32 and the positive class, it's still far better. It's not that the model is overfitting or something like that, right? And then finally you can see the variable importance plot. So the idea of this video is basically when you don't have a lot of data, right, you can run a neural network model, you can run LSTM, but it's not going to give you a lot of benefit. Sometimes it's not going to fit. You can still try it out, it may fit, but sometimes you want to fuse your structured data with unstructured data and basically see how it performs. So that you just want to quickly run through and see, like, you can also do it this way. Again, I used H2O, but you can use any of the packages you want to build the model. And that's it for now. In the next video, I'm going to see like how I can use the trained model and then show interpretation of the model for each and every feature importance. That's what I'm going to do in the next video. And that's it for this video. Thank you very much.